Okay, so let's do some examples. So we're going to work through some properties of the chain rule, and then we'll practice some substitution rule with integration, and we'll do some basic sort of interactions between the exponential and the logarithmic function. So first, let's look at a derivative. Suppose you get asked to find the derivative of e to the tangent of x. So the chain rule for the natural exponential function generally looks like this. D by dx of e to the anything is equal to e to the anything times the derivative of the anything. Now you don't have to remember this, but this is the form that every derivative involving an exponential turns into. Okay? So suppose we're given a derivative of e to the tangent of x. Well, this is going to be e to the tangent of x times the derivative of the tangent, which is just e to the tangent x secant squared of x. More often is to see integrals involving exponential functions. So suppose you were asked to integrate the integral of x e to the x squared plus 1 dx. So in a problem like this, you're going to be working with u substitution. That should be your first guess. So let's let u equal x squared plus 1 so that du is equal to 2x dx, and that's going to mean that 1/2 du is equal to x dx. Then this is going to get plugged into here, and what you're going to get is going to be 1/2 times the integral of e to the u du, which is easy because the integral of e to the u is just e to the u. And then you can substitute back in and make sure you do that to get 1/2 e to the x squared plus 1 plus c. Okay, so another example of a computation that you might see involving exponentials is factoring exponential type equations. So these are usually called generic quadratic equations. So you could get asked to solve a question like e to the 2x minus 5e to the x plus 6 is equal to 0. Now there's a couple of different approaches that you can take here. One standard approach that you see in calculus is to think of this thing as a substitution problem. Now it's not the same kind of substitution that you do as an integral, but you can still think of this thing as a quadratic if you figure out what this term right here is a square of, and is the middle term the square root of that. So one way to do this is to say, if you let u equal e to the x, then u squared is equal to e to the x squared, which is e to the 2x. And so with that substitution, this problem turns into u squared minus 5u plus 6 is equal to 0. And that's just a pre-calculus kind of exercise or an algebra exercise. U minus 3, u minus 2 is equal to 0. So u is equal to 3 or u is equal to 2. But of course, that's not what you were asked to find. You weren't asked to find u. You were asked to solve the equation for x. So you have to substitute back. That means that either e to the x is equal to 3 or e to the x is equal to 2. And then applying logs to both sides, you get x is equal to the natural log of 3 or x is equal to the natural log of 2. So in the world of generic quadratics, this is a quadratic form of an equation, even though it doesn't look like one until you make the substitution. Now you don't have to make the substitution. You could have skipped directly to this step, e to the x minus 3 times e to the x minus 2 is equal to 0 if you saw that. But you don't need to do that if you don't want. There's no special insight getting here. If you see something that you recognize as looking like a quadratic, don't be afraid to make a substitution to force it into the quadratic form so that you can use your algebra knowledge instead. So as a last example, let's look at a limit computation involving some exponentials. And what we're going to be taking advantage of here is the fact that the limit as x goes to infinity of e to the minus x, well, that's the same as the limit as x goes to minus infinity of e to the x. And remember, that means that the function is asymptotic at 0. So in case you don't believe me, e to the minus x is a function that looks like this. As you tend to infinity on the x-axis, this goes down to 0. So one of the basic facts of limit calculus is that the limit of e to the minus x is 0, and that comes up all the time. So let's see how we could use that. Calculate the limit as x goes to infinity of e to the 3x minus e to the minus 3x over e to the 3x plus e to the minus 3x. Now this is an indeterminate form, and you know it's an indeterminate form because what you have here is two pieces. This e to the minus 3x is going to 0, and the piece that's e to the x is headed off to infinity. So this is actually an infinity over infinity form. So infinity over infinity, which is indeterminate. So how do we usually deal with infinity over infinity? Well, we use L'Hopital's rule. But that's actually not going to do a lot of good here, because if I take the derivative of the top and the derivative of the bottom, e just replicates itself, right? The derivative of e to the 3x is just e to the 3x. The derivative of e to the minus 3x is minus 3e to the minus 3x. So we haven't made any improvements in the numerator or denominator. You could take derivative after derivative in the style of L'Hopital's rule, and you'll never get anywhere. So instead, the strategy is going to be to use algebra. What we're going to do is we're going to try to divide the top and bottom by the largest power of e that we see. I'm going to take the limit as x goes to infinity of e to the 3x minus e to the minus 3x over e to the 3x plus e to the minus 3x, and I'm going to multiply the top and bottom by 1 over e to the 3x. So this is a standard trick when you're computing these sort of rational limits. You would have learned this well before you ever learned L'Hopital's rule. What you get when you do that is 1 minus e to the minus 6x over 1 plus e to the minus 6x. And now, the fact that everything here is continuous means that you can shove this limit right up into the top and bottom of this expression. So where did this e to the minus 6x go as x goes to infinity? Well, it does this. E to the negative anything, as that power gets bigger and bigger and bigger, we're going to get close to the x-axis. So this term heads off to 0. Likewise, on the bottom, this term heads off to 0. So this limit, as you run out on the x-axis, is the quotient of two things that are tending to 1. And 1 over 1 tends to 1. So those are the basic computational ideas that we need for exponentials. In the next video, what we'll do is we'll take the logs and the exponentials that we've built out in the natural setting, so that is involving e's, and we will use it to build the big family of logarithms and exponentials where the bases don't have to be e. All right, see you next time.